So now again, how can we use that for dimensionality reduction? Well, let's reconsider the example before. Here we said, well, okay, we have these two concepts which are displayed here, and if we just reduce the first three features to one new feature and the last two features here to a second feature, we are good, right? And that is actually displayed here in the A part here, in the A matrix here. Yeah, and the strength here somehow tells us, yeah, the strength. What does it actually tell us? Well, it tells us more or less, spoiler, the spread of the particular concept or the particular new features. Yeah, so that would be the new features somehow, and that would be the spread, the variance of these new features, the strength of these new features. Now we have this thing here. Okay, first of all, we could of course use again three new features, yeah, which are displayed here in these decompositions. Yeah, so we could take again the A's here, but that does not display actually these two concepts. Well, it displays the two strong concepts in this very, very weak concept, which is weak because the corresponding value here in the S matrix is quite low. Yeah, so the spread is quite low, whatever, it's quite low. Yeah. So anyway, if we want to use it as dimensionality reduction, we could either use 3 dimensions here, which is even less than 5 original dimensions, or we could say something about, this is very, very small here. Why not omitting also that one here and just keep these two things here, which have a high value in S. Yeah, because in real world applications, it's probably even more noisy here around. So in that case, we may end up in K equals D. So we don't have any independent, so the rank is D. Actually, we don't have any independent rows, columns, submatrices here in the data set because the data set is too noisy. Yeah, and then we would have S as a D times D matrix. Well, then there is no dimensionality reduction. So as we do it so far, that we just keep the concepts that we will get from SVD. Yeah, so if there are just D concepts in it, according to SVD, we cannot reduce it from D to D. There's no gain, obviously. Yeah. So the question is, does the S values here tell us a little bit? I mean, they tell us the strength of the concept. So I already spoiled it a little bit. It is also somehow the variance of these concepts, and that makes sense. So if we go back to this one here, I mean, here the variance in this concepts, in these features here, is obviously higher than in this one here. Yeah, a little bit at least, and that is actually displayed here also. And the same holds true here. So the third concept, which is somehow around these two kind of noisy things here, have a very low spread, a very low variance actually. Yeah, and that is displayed here in this quite low value, at least compared to the other values here. So that is the idea, and now let's have a look at this actually works here. So well, obviously it works. So to reduce the dimensionality, we can set the smallest singular values in S to 0. Yeah, so we can set this guy here to 0 and then do the whole thing. So if we then just compute all that stuff here, the corresponding row in A transposed and the corresponding column in O would be erased, because if we set that to 0, all the corresponding rows here, columns here and rows here will be multiplied with this 0 here, meaning that they have no impact. Yeah? So that is the reduction actually. So setting this to 0 would mean that we omit this feature here, yeah? And the corresponding relationship of course also. Yeah, so we would omit with setting this to 0, we would omit the third concept, this artificial concept here, which has a very low strength, which would erase this one here actually. Yeah? So that is the basic idea. We don't do that here because the S values are quite high in both cases. Yeah, but we could also set this to 0, which would reduce the whole thing to the first. Yeah, actually to the first concept. So we would only model then this concept here with this feature, this new feature, if we set this to 0 and would omit this second concept here, which is this feature actually. Yeah? So that is the basic idea. We could do that, and that probably only makes sense if the value is close to 0 or very small. Why is that the case? Well, we'll see that the values in S are actually the variances along the eigenvectors, the new features squared. Yeah. We call them the energy. Yeah, we should retain enough singular values, so those S values are called the singular values, and they are actually squared, the squared variance along the features. Yeah, we talk about the energy of the singular values, and we should retain or keep enough singular values to make up 90% of the energy. So that is the 80 to 90% rule of thumb, as we got to know it before with the PCA actually. Yeah. So the energy is defined in terms of the singular values. So in the previous example, the total energy of our matrix S here would be the singular values squared, the sum of the squared singular values actually. Yeah. So it would be 12.4 squared plus 9.4 squared, and so on and so on. Yeah, so that would be the total energy. And if we set this one to 0, we would keep only the first two, which is this one here. So the first two would already make more than 99% of the total energy of the singular values. So in that case, it is more than 80 to 90%. So we would be safe, so to say, to as a rule of thumb, to keep only those two concepts still in this data matrix here. Yeah? So setting this one to 0 once again would lead to actually all of those values here in the third row would be multiplied with this 0 here, which means that they get 0. Yeah? So setting this value here to 0 would actually omit this third feature. Yeah? And the two first features actually are the subsummations of the first three original features and the last two original features, as before in the example before. Yeah, so that is the basic idea, and that you see that PCA is actually a special case of SVD, or other way around. SVD is a generalization of PCA. We take a closer look at actually the decomposition of the covariance matrix. Yeah? So we have the covariance matrix, which is computed by the original normalized data matrix. Yeah. So and SVD actually decomposes our data matrix in these three matrices, O, S, A transposed. So if we take the covariance matrix, which is D transpose times D, and just fill in this SVD decomposition, meaning that D can be rewritten as O times S times A transposed. We have instead of D transposed, we have O times S times A transposed, and in terms instead of D, we have O times S times A transposed. Yeah, so we just replaced D by O times S times A transposed in this formula here. Yeah? So that is how we get or how we can compute the covariance matrix. Yeah? So transposing means that we just take it the other way around, so to say, and transpose everything. So instead of taking O times S times A transposed, if we transpose this in this brackets here, then we get the reverse order transposed. So we get A times S transposed times O transposed, which is this one here, and the rest remains the same here. Yeah. And now we use a little bit of different bracketing here, so which we can do because we can compute this matrix multiplication in any order. So we can also first of all compute O transpose times O. Well, if you have a closer look at O is an orthonormal matrix, so O transpose times O is actually the identity. Yeah? So we have this one here comes down to, since this is the identity, it comes down to, so we can omit that, we can it comes down to A times S transposed S times A transposed. S is a diagonal matrix, so transposing has no effect. So S transposed times S is the same as S squared. So the whole thing runs down to A times S squared times A transposed. Yeah. So in the end, we have the covariance matrix. That was our starting point. So the covariance matrix can be decomposed by SVD into two matrices, actually, A and something in here which is S squared, and that looks pretty much like our PCA decomposition. So we have the eigenvalues in here, yeah, and the eigenvectors, the corresponding eigenvectors here and here. So the A's are obviously the new features. That's what I told you before. So the A's here are the new features. Yeah. So for example, this row here is the new feature that summarizes the first three features here that are connected to our first concept, and the second row is the summarization of these two features here that are connected to the second concept. And the same holds true here, of course, with this one here. Yeah? So that is the formal somehow derivation that this is actually true, and the singular values are the squared eigenvectors actually. Yeah? So that is the connection between SVD and PCA. So you can use SVD in order to compute the principal components, so the eigenvectors and the eigenvalues for a data matrix. Yeah? You just have to apply SVD on the covariance matrix in order to compute the PCA, the principal components of your data set, yeah? Your normalized data set in that case.